All right. My talk is about how to read academic papers, not just for fun, but also because we want to take the ideas and the mathematics in these papers and turn them into code that we can actually run. Now, maybe you've tried to read a paper before and you got stuck, or perhaps you were overwhelmed by all the mathematics and the jargon. Or maybe you've never read a paper in your life and you're wondering why you should. Well, I'll tell you why you should. Papers are where all the interesting ideas are. They are a great place to learn about the state of the art in your field. And in fact, a lot of the knowledge is only transmitted through papers. There are books, of course, but books usually lag behind a few years. So if you want to be on top of things, then papers are where it's at. Unfortunately, academic writing isn't always very easy to read, especially if you're not in the academic scene. Now, I'm not a mathematician, I'm not an academic, I've never written a paper in my life. I'm just a self-taught coder. But I did work as a machine learning engineer, and as part of that job, I had to learn how to read research. And so these skills came in quite handy when I switched to audio, because I can finally understand things now. So in this talk, I just want to go through some tips and tricks on how to make the most out of papers. And because they're kind of similar, I also want to talk a little bit about patents. Now, first of all, where do you even find papers? So the goal of an academic is to do some really cool research, write a nice paper about it, and then hope that a journal will officially publish it. The more prestigious the journal, the better for your career. Another way to get your work out there is to present it at an academic conference. And so on the slide, I've listed a few of the main journals and conferences for audio, but there are many more. But there are way more papers being written than there's room to publish. So in a number of fields, it has become the norm to upload certain so-called preprints of your work. And you can think of a preprint as like being a beta version of a paper. On the website archive.org with an X, you can find a lot of these preprints, especially for machine learning, because that field just moves way too fast for journals to keep up. So two great search engines for papers are Google Scholar and JSTOR. So if you want to find a paper, you can go there and you'll probably find it. The bad news is that most papers, or a lot of papers anyway, are locked away behind paywalls. And that can get quite expensive. You can easily pay $30 per paper or more. You could subscribe to all the journals you're interested in, but that also becomes quite costly. So I've got a bit of a tip for how to find papers for free, even if they're behind a paywall, and that is to Google it. Just Google the name of the paper, put PDF behind it, because often somebody will have downloaded the paper from behind the paywall and put them on their own personal website, and that got indexed by Google, and you can still find the paper for free that way. Often it's actually the author of the paper that has the paper on their own website. It's just usually some like academic website that's not easy to find. So Google can often find a lot of these papers. A conference like DevX will also upload their proceedings for free. And the proceedings are basically like a huge PDF file containing all of the papers that were published at that conference. Not all conferences do this, but quite a few do. So that's also very nice. If you can't find a paper anywhere else, you can always just email the author of the paper and ask them to send you a copy. No guarantees, but it never hurts to ask. And I think most authors are happy to do this. Once a paper has been published, it's assigned a DOI, or Digital Object Identifier, and that's the link that you see here on the slide. A DOI is just a unique URL to the paper. So if you were to click this link, it would take you to like a landing page for the paper. And you still might hit a paywall there, or you might hit the direct download. But just between us, there are certain unsanctioned download sites where you can basically find anything you want if you know the DOI for the paper. But you did not hear that from me. So if you're getting serious about reading and collecting papers, you might want to use some kind of tool to organize them. I use this thing called Papers from a company, ReadCube. It's not the best app I've ever used, but it's okay. Some other apps are Mendeley and Zotero. And the nice thing about these apps is that they let you add highlights to your papers, or they let you add notes, or you can organize the papers in categories. So that's a lot nicer than just dumping a bunch of PDF files in a folder somewhere. So I recommend getting an app like this to organize your paper collection. All right, some uncomfortable facts about scientific research. First of all, papers are not written for beginners. They are written for other academics who are already experts in their field. So, for example, if some new paper comes out that's like about some new cool reverb method, it's not going to be like a complete beginner's guide to reverb. Usually the only thing that's explained in detail in the paper is the new idea that this paper is about, and anything else is stuff you're already supposed to know. Second of all, not all academics are good writers. Some papers are just not very clearly written, even if the ideas in the paper are pretty good. Like I said, there's like lots of jargon, lots of formal language, typically lots of passive voice, sentences that are hard to follow. So if you're having trouble reading a paper, it might not be you, it might just be a badly written paper. Also, believe it or not, papers may contain mistakes. Now, before a paper gets published, it goes through this rigorous vetting process known as peer review. And once a paper has been published in a reputable journal, you can be pretty sure that most of the bugs have been taken out. But if you're reading a preprint, for example, it won't have been peer-reviewed, and not all conferences do peer review either. And just to show some examples, even well-known papers will have mistakes. So this is the Blit paper by Stilson and Smith. And when I started reading this, I got pretty confused about this math notation here, especially those double arrows. No idea what that meant. Turns out there needs to be a minus sign. So if the math is confusing, it might just be a problem with the typesetting in the paper. Another example, this is from Chowning's famous paper about FM synthesis. This is from 1973. Back then, they did not have PDF files, so somebody was nice enough to scan in the original paper from a book or a journal or something. That's the one on the left. And the one on the right is somebody made like a proper PDF version of this. And that's the one I started reading, and I got really stumped on these math equations. It says sine A minus comma S. That doesn't look like proper math to me. But in the original paper, that's sine alpha minus beta. So you have to be careful about these modern-looking PDF versions of classic papers, because somebody had to type it all in or OCR it, and they probably made mistakes, particularly in the math. So you can't always trust anything that's in a paper. All right, so a little while ago, I made a plugin called Crunch. That's like a combination of a low-pass filter and a saturation effect. It's open source, it's on GitHub, check it out if you want. But the main technique used in this plugin is something called the €1 filter. And I had heard of this €1 filter being used by other people in other places to smoothen data. And I was just curious what it would sound like when applied to audio. So as a real-world example of how to read an academic paper, why don't we go through the paper that introduced this €1 filter together. So the main idea when you're reading a paper is to look for the big idea. Usually a paper only introduces a single new idea. Usually that's just a variation on something that already existed. And the rest of the stuff in the paper is just like background information, experimental results, and so on. So the takeaway here is that you don't actually need to understand everything that's in the paper. You don't even need to read everything that's in the paper. You can all skip all the unimportant bits. Of course, then the key is to learn which bits you can safely skip and which are important. So let's go through this paper as if I was reading it for the first time, and I'll tell you how I approach it, since I think, for most of you, this will be the first time you will see this paper. Right, so it starts with a title. The title here is the €1 filter, a simple speed-based low-pass filter for noisy input in interactive systems. Quite a mouthful, but that's typical for these paper titles. This particular title is actually a pretty good summary of the entire paper, but you kind of need to read the entire paper first before the title makes sense. Below the title are the names of the authors. So here we have 3 authors. Usually the first one is the principal or main author. There's often also contact information for at least one of the authors. So if you have any questions about the paper, just shoot them an email. It's their own fault. They put their email address in there. One of the questions you might want to ask is, do you have any source code for this paper? Because maybe they do. So the first part in the paper is the abstract. And this is really like the sales pitch for the paper. So ideally, the abstract summarizes the paper, and it will also highlight the new idea that this paper introduces. Now, if you read this, I'm sure you'll agree that this one is actually quite readable, which isn't always the case. But this abstract uses some terms you might already know, such as like a first-order low-pass and cutoff frequency. There's some terms in there that sound vaguely familiar, maybe, like jitter and lag, but the abstract doesn't always explain everything. It's just from this abstract, we can get the sense that the main idea or the big idea in this paper is like a low-pass filter that has an adaptive cutoff frequency. So that's like the whole thing that this paper is about. Now, sometimes the abstract doesn't make any sense until after you've read the paper, because it introduces new concepts or terminology that aren't explained until somewhere in the paper. So don't always judge the quality of a paper by how well the abstract is written. Sometimes the abstract is just there to remind you, like, what was this paper actually about, rather than, being a good sales pitch for why you would want to read the paper in the first place. All right, so before reading the paper in detail, I'd just like to scroll through it from top to bottom, just to get a sense of what's there, what's the structure of the paper like, how is it built up, how much math is there in there, and so on. You don't need to read all the stuff that I'm putting up here. I'm just highlighting the different parts of the paper. Most papers follow like a similar kind of outline. It starts usually with an introduction, and the introduction explains the problem they are trying to solve. So for this particular paper, the problem is that they want to smoothen data coming from interactive controllers, like a Kinect, for example. And the user might be moving slowly or they might be moving fast, and they want to change the way the filter works so that they can capture both high-frequency information, but they can also capture low-frequency information while reducing noise as much as possible. So that's kind of what they explain here. That's the problem they're trying to solve. And they also give like a high-level overview of their solution, which is the €1 filter. But they don't really show a lot of details yet. It's always a good idea to read these introductions because they set the stage for everything that is to follow, even if the details are still a bit sketchy at this point. The next up is a section where they talk about related work. So these are previous techniques that you may have used to solve this particular problem. And this is something that happens, you'll find in most papers, because it puts the invention from this paper into a context. And basically here they are saying, our stuff is actually going to be better than these guys. So here I see something about a moving average, which I happen to know. I see something about low-pass filters, sure. I see something about Kalman filters. I'm not that familiar with them, but that's all right. I don't need to understand everything that happens here exactly. I just need to get some sense of other techniques that have been used to solve this particular problem. But it's clear that from this paper, they are saying that their solution, this €1 filter, is probably going to be better than these previous methods, or being advantageous in some way. Now, it's very useful to read these kinds of background sections, especially if you're new to a particular topic, because they always summarize important previous work that you might not be aware of. So it's good to read it. It's okay to skim it through as well. You don't need to understand everything. I don't need to understand this Kalman filter thing in order to keep reading the paper. Then we come to like the meat and potatoes of the paper, the stuff that we are most interested in. And this is where they explain their solution into a lot of detail. Right now, I'm just still skimming through the paper. I don't need to read everything in detail yet, but I see there's some math here. Not too much math, fortunately. It doesn't look too scary, but I'm not too worried about exactly understanding what's going on here right now. I just wanted to know, like, where in the paper do they start? Where do they explain their solution in detail? And this looks like it's it. So this is probably something you want to come back to later. Then there's a section where they compare this €1 filter to the older techniques that were mentioned earlier, such as the moving averages and the Kalman filter and so on. There's like a pretty graph with some test results. And this is where they put their invention to the test. And a good paper will have this kind of comparison section, because without it, you will just have to take their word for it that their solution is better. I mean, you still kind of do need to take their word for it, but at least if you wanted to, you could try to do a similar comparison yourself, and you should get similar results. But it's also perfectly fine to skip this part of the paper if you're not interested in this. It's useful to come back to later if you're writing code and it doesn't seem to work and you want to know what sort of results you are supposed to be getting. And then finally, there's a conclusion, which, to be honest, often just repeats the abstract, but in different words. And then there are the references. Now, a good paper will have like tons of references to previous work. So for example, I mentioned that I was only vaguely familiar with the Kalman filters. So here I repeat the bit from the background information section. And it has this number 8 between square brackets, and that actually refers to a paper number 8 from the references. So if I wanted to learn more about this stuff, I could go presumably read that thing, and it will tell me more about what these Kalman filters are. Now, sometimes a paper makes no sense at all. That really means you should take a step back and read some other papers first, because you're missing some of the prerequisite information. And to figure out which papers to read, you can go to the references section to find the previous work that you might need to brush up on first. Now, conveniently for our purposes, this particular paper has an appendix with source code, or at least pseudocode. If all papers had pseudocode, I would not need to give this talk. So it's a good idea to always like scroll through all the way to the end of the paper, past the references to see if there's an appendix with additional information that did not fit into the main text. Some papers also have a supplement, which is a completely separate file. It's a good idea to also Google for the name of the paper, put supplement behind it to see if they have such a file with more information. All right, so this was a very quick run through this paper. It's short and sweet paper. This is only 4 pages, so I picked it because so it's not too overwhelming. But even if a paper is longer, the main idea still usually fits onto a page or 2. And everything else in the paper is just there to build a story around that. All right, so I hope you've got some sense of what this paper is about. I wouldn't expect anything more at this point. We just scroll through the thing top to bottom just to get a feel for what's in the paper and what to expect. But in summary, this particular paper had this particular structure, but most papers roughly follow this structure. But like I said, you don't need to read everything, you don't need to understand everything. The trick is to figure out, how do I cut through the noise and extract the parts of the paper that I'm interested in, and how do I ignore the rest? All right, so before we go and implement the algorithm from this paper, I want to do a quick crash course in mathematical notation, because it's important to know a bit about math, because papers express their ideas in math. And I know from talking to people that the math part of the papers is often the problem. It's like the language, the jargon, but also especially the math is what people tend to have problems with, because we might be programmers, but that doesn't mean we have like a solid math background. Now, sometimes papers have pseudocode, like this particular one. If we're really lucky, we might get like a MATLAB or Python implementation. But typically, there's no code, especially no C++. So it's good to be able to read these equations, to not be afraid of them, and to write the code ourselves. Okay, I'm going to do this quite fast because I've got a lot of stuff to go through. These things are variables. I'm sure that's no surprise there. Now, as software developers, we've been taught that single-letter variable names are bad, but I don't think anyone ever told the mathematicians. These things are also variables. This is the Greek alphabet, or at least part of the Greek alphabet. These are like the most common symbols you might find in typical DSP papers. It's worth learning the names of these letters because that makes it a lot easier to read equations. So for example, earlier I showed this. If you know that this symbol means alpha and the other symbol means beta, then when you see this equation in your mind, you'll read it as sine alpha minus beta instead of sine weird thingy minus other weird thingy. And that just makes it a lot easier, to comprehend what's going on there. Now, a lot of these Greek symbols have specific uses. For example, alpha and beta are like the foo and bar of mathematics. So if a mathematician doesn't want to think too hard about which variable name to use, they'll typically use alpha or beta. Delta is often used for like a difference between things. Epsilon is also often a small value. Omega is, in DSP, would be like a frequency. Mu would be the mean. Sigma would be like the standard deviation or spread. Tau is often used for like a time amount. I don't know if you're starting to discover a pattern here, but I said, delta is difference, mu is mean, sigma is spread, tau is time. That's not a coincidence. That's actually how these Greek symbols are often chosen. So if someone's writing a paper and they need a variable name for something, they will pick like the English word, use the first letter, and then substitute that with the Greek symbol, because Greek symbols look cooler, I guess. But that's really often when you encounter a Greek symbol, just in your mind think like what variable name or what concept does this relate to? Because if you see the Greek symbol mu, that's kind of a weird symbol if you're not used to it. But in your mind, if you translate that to the letter M, then you might think, oh yeah, that corresponds to the mean. So that's a little hint to make it easier to map these Greek symbols to like concepts from the paper. It does sometimes lead to confusing situations. This is an equation from a machine learning paper. So this has the symbol pi in it, which you probably recognize, but this is not the pi that you know and love. This is not 3.14 and so on. This pi represents a probability because the word probability starts with a p and the Greek version of that is pi. So even though these symbols are often used for specific purposes, it's not always the case and you really need to be aware of the context. Okay, a bit more about names. These all say X, but they mean different things. So the uppercase version of a variable is often used as like a transformed version of the original. So, for example, the uppercase x might be the Fourier transform of the lowercase x. If you need more than one uppercase variable, you might use a different font. So that's like the squiggly one. But sometimes, there's other variation as well. There's like x with a little roof on top, known as x hat. There's x with a star, or with a tilde, or with a bar on top, or with a single quotation mark, also known as a prime, which might know the prime one from calculus, where it means a derivative. But in general, it just means that this is some transformed version of x. Now, which of these symbols is used in the paper is pretty arbitrary. It just depends on the author and whatever they feel like using. The reason I'm pointing this out is that I don't want you to feel intimidated when you see a symbol like this, because all of these say that this is x, but different somehow. Now, variables can also be made up of multiple values. In programming, we call that like a vector or an array. So here I have an example, something called capital X. It might be like a digital audio signal, and this is made up of individual samples that are called lowercase x with a subscript or with an index. And so here I'm using this distinction between capital X to mean the whole thing and lowercase x to mean the things inside of this particular vector or array or something. Other people might use, instead of a capital X, you might also see like a bold font or maybe an X with a little arrow on top. There's different ways to notate this. The reason I'm showing this is that for some strange reason, mathematicians like to start counting at 1 instead of 0. And so the last element in this list would have index n, and the letter n is often used to mean like how many of something there are. Could be capital N, could be little n. But when you read the paper and you turn it into code, be careful, because sometimes they do start counting a 0, and you might have strange off by 1 errors if you're not careful. Now, there are different ways to notate indexing for when you have more than one of something. You've seen like the subscript notation here on the left. It's possible to have more dimensions than one, so you also need more indexing variables. And typically, these are called I, j, and k, but be careful, because I and j might also mean the imaginary number. Sometimes, instead of using a subscript, they put the index above the variable, so it would be a superscript. But that's confusing, because that's also the notation for taking the power, so they might put little parentheses around it. And sometimes you have a subscript above and below, or they do it like we do in programming with the square brackets. So all of these things are basically equivalent ways to notate indexing, and whichever one the paper uses really depends on whatever they felt like writing. This is just to say that math notation isn't very strict. Lots of different authors have different styles, and you should really think of math notation as being like a shorthand for expressing mathematical ideas. It's not really a formal language like a programming language. So you need to be a bit flexible when reading these math equations, and it's not always obvious what they mean. Okay, a few more symbols. This is the capital version of the Greek letter sigma. It looks like an E, but it's actually an S. And we use the symbol when we want to calculate the sum of something, because sum starts with an S, and that's the capital Greek letter S. So whenever you see this, think of a for loop. So as a quick example, this would have this is a loop. It has a loop counter little n. It goes from 0 to n capital N minus 1. So the starting index is at the bottom, and the ending index here is at the top. So the ending index is inclusive, so this loop actually repeats capital N times. Now, inside this loop, I do something with the sine wave. It doesn't really matter so much, but you can see that there are some additional variables inside this loop. So there's like A, omega, and T are being used. I'm doing this to show you that the value of this A variable actually depends on the loop counter, because it's being indexed by the loop counter N. So what exactly does this all compute? Well, I'm just going to show you the code, because that's a lot easier to understand. It's just a simple for loop that repeats n times. And whatever we calculate in each iteration of the loop just gets added to a sum variable. So this whole thing is just a simple sum reduction, like they would call it in functional programming. If you've never seen this particular symbol used before, you might freak out and like, oh, this math stuff is too difficult for me. But it's actually it's just a little for loop, super simple. It's just that if you're not used to seeing the symbols, you might get a bit intimidated. What I want to point out in this talk is that all these symbols have pretty simple operations behind them. And once you understand that this, for example, is a for loop, it becomes a lot less intimidating. You might also see this, where you have like 2 for loops. Of 2 is these sigma symbols. This is actually just like a nested loop. So here we have an inner loop with index j, and that whole inner loop is repeated for every iteration of the outer loop. As you can see in the source code, super simple, it's just a for loop inside of another for loop. But this also shows that math notation is used in these papers because it's a lot more compact than the source code. I'm sure all of us programmers, we would love to see source code instead of math, but papers will become a lot bigger. And the idea behind math is that we want to express as much as we can with as few symbols as possible. So that's why you see stuff like this in papers rather than source code. Something you might also see is a variation on this. This uses the capital Greek letter pi. This does the exact same thing. This is also a for loop, but now here the results of every iteration are not summed up, but they are multiplied together. So this calculates alpha 1 times alpha 2 times alpha 3 and so on. And the reason they use a capital letter pi is because this computes a product which starts with the letter p, and that's pi. All right, so something you might encounter a lot in papers as well is an integral. The symbol at front is like a stylized S. And that's because an integral really calculates like a kind of summation. And I just showed you that this is also a summation. So whenever you see the integral, you can actually think, the bottom one. They're not exactly equivalent, but they are. When we like implement integrals in code, in DSP code, we will actually do like the bottom one where we simply add up the different samples in the signal. So for our purposes, integrals often just turn into these sums, and we know that these are just for loops. There's also this, the opposite of integration, which is differentiation, and there's lots of ways that this gets notated in papers. Looks very scary, but where integration is adding up samples in a signal, differentiation is simply subtracting samples. So the symbols might, the math might make it look very scary, but it actually turns into pretty simple code in the end. And there are lots of other symbols you might encounter in papers. There's this Wikipedia page, which is a good overview of most symbols. The main point I want to drive home here is that, we see this math and we're like, ugh, I have no idea what any of that means. But it's really just like a very compressed way of representing information. So if you want to figure out what an equation does, you kind of have to decompress it in your mind, figure out what all the symbols mean, and you can do one by one. I just like to write a bit of code for myself to explain, what does this symbol do, what does that symbol do. So don't be too scared off by scary-looking math, because in the end, whatever happens beneath all these symbols actually turns into code that you can actually understand. Final bit about math. You don't need to read or understand all the math in a paper, so this is apart from a paper. There's a whole bunch of integrals here. These are just there because the author wants to explain how they got to their solution. It's nice if you can follow along with all these integrals, but you don't have to. The important part is the formula at the bottom here, and that doesn't look half as scary. So, like I said, often you can skip a lot of the math, and you just need to look for the one piece of information you actually need to use. All right, so now that we've leveled up our math skills a bit, let's go back to this €1 filter paper and see what kind of math it has to offer us. So normally I would scroll back to the beginning of the paper and I read the introduction again in more detail and the background information in more detail. And it's fine if there's still things I don't really understand, as long as the picture is slowly becoming clearer, right? Most of the time you will need to read a paper multiple times before it starts making sense. It's common to find yourself going back and forth through the paper a lot. This is is normal. It happens to everybody. So don't think you're like super stupid if you don't understand a paper completely upon first reading. You really need to study the paper. Sometimes even like a single paragraph, you just need to go through it a whole bunch of times before everything makes sense. All right, so here's the math from this €1 filter paper. The numbers on the right there are just there to give each equation a unique number, so the paper can refer to like equation 4, for example. It means that I skipped over 3 equations here, 1, 2, and 3. These are all in the background information section of the paper, but these 4 are in the section that talks about this €1 filter in detail. So presumably these are all that we need. Now, this math doesn't look too scary to me, but there are some symbols in here that I don't really know what they mean. For example, alpha, or this X with a little hat on top. So in order to understand what they do, we need to refer to the text. So usually all these symbols, or most of the symbols, will be explained in the text. So let's bring in some of the surrounding text and see what it says. Now, you don't have to read all this. I just highlighted a few things. At the top, it says, the 1 euro filter adapts the cutoff frequency of a low-pass filter for each new sample. All right. According to an estimate of the signal speed or its derivative value. So apparently, we will need to calculate a derivative somewhere to set the cutoff frequency of this filter. It also mentions we should rewrite equation 1. So I skipped over equation 1. So let's go back a little bit further and bring in that equation to see what it does. Now, this is equation 1. It's from the background information section of the paper. It's from the section where they talked about low-pass filters. Now, this, fortunately for me, is something I understand. This, and I'm sure most of you here will understand this too. This is like a simple linear interpolation between two values. Now, the text explains that the symbol capital X with the little I is the current input sample, and capital X with the little hat on top is the current output sample. So here we have this distinction again between X with a hat and X without a hat, where X without a hat is like the original data, and X with a hat is the processed data. The subscript I is like a timestamp, so it would be like a sample number. So that means that here, like capital X with a little I is actually a single sample value. So previously, I showed you an example where I had this like digital signal that I called capital X that had like lowercase x's inside of it. But here they call like the individual samples, they call capital X. So why do they write capital X instead of lowercase x? I mean, I have no idea. This the choice of these authors of this paper. It doesn't mean that something always needs to be written in a specific way. Math notation is all over the place. And for some reason, they decided to call individual samples the capital X. So from now on, if we're reading this paper, if we see like a capital X, we know that this is the current input sample, and capital X with a little hat would be the current output sample. Now, this formula is actually an IIR filter because it uses the current input sample at time I, and it uses the previous output sample at time I minus 1. And I'm sure you've seen this kind of formula before. This is just like a simple one-pole low-pass filter. And the text also says that alpha is a smoothing factor or filter coefficient. I hadn't seen the notation with these square brackets before, so I looked it up on Wikipedia, and it told me this is a half open range. So alpha is some value between 0 and 1, but it cannot be 0. In any case, if we go back to our equations, then we see that equation number 4 is actually the thing that calculates this filter coefficient alpha. So I now know, from reading the text that alpha is actually the coefficient for a filter. And here we have a formula for how to calculate it. Now, of course, this formula has some symbols in it that we haven't seen before. So there's a symbol tau. We actually have an equation for that. This is equation number 5. And there's also the symbol capital T with a little e. There's no equation given for this capital T thing, but the text tells me that this is actually the sampling period, so the time between individual samples. And I could have known this because in DSP, we also use the letter capital T for this. But they add this little e as a subscript to indicate that in their setup, time between events can vary. Since I want to use this to do audio stuff, I'm just going to say that this TE is like 1 divided by the sample rate. And then we move on to the formula for this tau. This is like a very DSP-looking formula. It has like 2 pi in it, and pi really means pi here. It also has the symbol FC, which I'm going to guess stands for the cutoff frequency, which is also the typical symbol we use for that in DSP. And it makes sense in the context of this paper. But what I want to point out here is that this C is actually part of the variable name. So this is actually like a 2-letter variable name. The F stands for frequency, and the C stands for the cutoff frequency, as opposed to some other frequency. And again, this is how math notation can be a bit ambiguous, because sometimes the subscript is actually like an index. For example, we saw X with the I, and the I would be like a timestamp there. But here, the C is actually just part of the variable name. So you have to be kind of pay attention to what do they actually mean with a subscript. Equation 7 then gives us the formula for calculating this FC, and it contains like two parts. There's FC min, which I'm going to guess stands for like the minimum possible value for FC. So here we actually have like a 5-letter variable name. And then it does beta times something scary looking. Now, if I go through the text, it tells me that this FC min and beta, there's no equations given for it, so I have to go through the text to see what they mean with this. And these are like 2 user configurable parameters for this algorithm. So these are things you might want to like hook up to a knob in your UI, for example. I mentioned them because I wanted to know what the units were of these things, and the paper doesn't actually mention anywhere what it is. So I kind of was able to deduce that these are in hertz, which it makes sense because cutoff frequency would often be in hertz. But the point is that the paper doesn't explicitly mention it anywhere. So what I'm doing here is I'm just going through these equations, and I'm trying to figure out what all these symbols are, trying to look at all the different parts in these equations to see if I understand them. I bring in the text if I need to get some more information, figure out what they actually mean by it. Also, bring in some of my DSP background knowledge to make sense of it. And slowly my understanding of how these equations are working and what they're doing and how they fit together is building up. But there are still some mysteries here, like this last bit here. This says X with a hat, but it also has a dot on top. And that's not a mistake. So we actually have different symbols. We have like a regular X, we have X with a hat, and now we also have X with a hat and a dot. And so these are 3 different symbols, but it's like you have to really pay attention. Like, is this regular X with a hat, or am I talking about X with a hat and a dot now? So it's not always super clear that this is actually like a different thing. But we also have no equation for calculating this X with a hat and a dot. So again, we look in the text and we get like 2 whole sentences to explain what it is. Here it says that X with a hat and a dot is derivative, or the speed of the signal. Now, remember earlier it said something about we need to calculate a derivative to figure out what the cutoff frequency of this filter is. So that's probably this one. And it says, how do we calculate this? It says it's computed from the raw signal values, and then it's low-pass filtered with a cutoff frequency of 1 hertz. Now, it's maybe not super obvious, but we are actually dealing with 2 low-pass filters in this algorithm, right? So there's the 1 filter itself, which has a adaptable cutoff frequency. But there's also this other low-pass filter that we need to calculate this derivative. And this is the only mention of it in the entire paper, just these like 1.5 sentences. And this is really typical for academic papers. There's a lot of information packed in just a few sentences. And it's really easy to overlook like a crucial detail like this. And it's typical for academic writing, but this is why you have to, once you start implementing this paper, actually start writing the code, you might be stumped, run into something like, oh, I need this derivative, how do I calculate this? You have to go through this paper like line by line and really read every single line to make sure that you understand where this comes from and how it works. So you have to pay attention when reading these papers. All right, so the last equation that we didn't look at yet is equation number 6, and this has a few symbols in it that we've seen before, like capital X at time I, and also X with a hat at the previous timestamp, I minus 1, and it calculates X with a hat at the current timestamp. So this looks like a filtering formula again, and this seems to be the equation that puts the whole thing together. And we could implement this as it's written here, but I want to point out a few things. First of all, these equations are actually in the wrong order. It makes more sense to put them in this order, because we start with the cutoff frequency, then we calculate tau, then we calculate this filtering coefficient alpha, and then we do the filtering. So it would have made more sense to me to present them in this order. So don't assume that equations are always in the logical order when you read a paper. Also, this equation 6 bothers me. First of all, there's this thing at the end. That's actually the same thing as alpha, so why not write it like so? But also, this calculates X with a hat. And we've seen before that we had this one-pole filtering formula from equation 1 that also calculated X with a hat. And this doesn't actually look like any filtering formula that I know. So I was wondering when I was reading this paper could this equation 6 be the same thing as equation 1? And I'd love to show you how I got there, but I don't have time to do all the math here. But if you work it out, then equation 6 is actually the exact same thing as equation 1. So again, I don't know why they didn't just write it like this, because to me, this is a lot easier to understand than that equation 6 that they gave before. It doesn't really matter for the purposes of the paper because they're equivalent. They calculate the same thing. But at least I understand what's going on now. And that's really, my goal of this talk isn't really to talk about this filter in particular. It's interesting, but not that interesting. But I just want to show you what it takes to go through all these equations and figure out if there are parts you don't know. You might want to pull an equation apart and just look at that little thing to make sure you understand it. And then see if you can simplify these equations until you get something that actually makes sense to you. So just in case you're interested, this equation number 6, or really equation number 1, is just the regular one-pole filtering formula that's used all over DSP. So the only thing that's different here for this €1 filter is how we calculate the filtering coefficient alpha. And ultimately, that's dependent on the derivative of the signal, because in equation 7 there we have that x hat with a dot, which is the derivative. And a derivative really describes how fast the signal moves. So in this case, if a signal moves fast, it means like, if the user is moving quickly, then there's also high frequency information in our signal. So we want to put the cutoff frequency of our filter high. But if the movement is slow, then we can put the cutoff frequency much lower to filter out all the noise in the system. But we still keep like the original, or as much as the actual data as possible. And that's really the whole thing that this computes. And we have that, the beta in equation number 7. It's just there to set like the sensitivity of the system, like how much does the cutoff frequency change depending on the speed by which the signal moves. Now, very quickly, I want to write the code for this. We can do it very quickly because these equations are quite simple. So this is like this a very standard one-pole filter implementation again. I renamed the variables. So x with the hat, I actually turned it into y because it's, that's more like how we would write it in DSP. We can calculate this alpha, which is the filtering coefficient. Note that I said that this TE symbol, that stands for 1 divided by the sample rate, so we can simply write it like so. And then we can add the formula for tau. Note that I don't really like that 1 divided by stuff, so with a little bit of algebraic manipulation, I can write it like so. This is equivalent, it calculates the same thing, but this is something you might find yourself doing when you convert code from a paper into DSP code, because just because it works okay in math to do something like 1 divided by stuff, that might not be the optimal way to write it in code. So you might find yourself doing these sorts of optimizations. And then we add the formula that calculates the cutoff. And now we have these equations 4 through 7 from the paper again. Just the one thing I don't really know yet is how to calculate this derivative variable. That was like the x with the hat and the dot on top. So I do know that the text told me that this comes from this like second low-pass filter with a 1 Hz cutoff, so I can write that already. But I don't know what goes into this filter, like this dx variable at the top. So the problem is the paper doesn't actually tell me what goes into it. In those 2 sentences that told us about this derivative, it just said that the derivative is calculated from the raw input signal, but it doesn't say how. So I know that a derivative is when you take like the difference between sample values. So I could write this maybe as like a dx is like the current input sample x minus the previous input sample x, which would make perfect sense to me to calculate a derivative, but I don't know if that's correct. So I'm a little stuck here, but I did remember there was pseudocode at the end of the paper. So that's this. If you've never seen pseudocode before, it's basically the same thing as like a programming language. It just doesn't compile. And the little arrows here are used for like this, like the assignment operator, but it's pretty easy to follow. I'm sure you can read this just fine. The one weird thing is that now instead of using the Greek symbols, they had to use text. So something like x with a hat, they call now hat x, for example. But we already implemented these 3 lines. That's the C++ code we just wrote. And fortunately, there is this line 5 that tells us how to implement this missing bit that I didn't know how to do. And it does indeed take the current input sample x and subtract something from it, but it's not the previous input sample, it's actually the previous output sample. So I wouldn't have guessed that at all. But they also multiply it by the sample rate, which is also something I would not have guessed. So the reason I'm showing this is that, a key detail of this algorithm is hidden somewhere in an appendix in the paper. It's not mentioned anywhere in the paper itself. There's no equation given for this particular formula, and it's pretty much like the most important part of the entire paper. And this is actually not unusual. Many papers leave out these key details, and implementing the paper then becomes a bit of a guessing game. And if not for this pseudocode, I probably would have implemented it wrong, and the whole thing might not actually have worked. So we can finish our source code, and it turns out it's actually pretty simple. After all this work of studying the paper, we finally got something that can run. But the takeaway here is that it wasn't always obvious. Some parts were confusing, some info was missing, or hidden, or maybe even misleading. And the whole thing was a bit of a puzzle, even for such a short paper. And actually, I didn't even get this far. I had to go on Google for help. And fortunately, some people had written some blog posts where they explained how this paper worked in more detail. So I would recommend, if you are trying to implement a paper, to read it for yourself first, try it for yourself first, see how far you get. If you get stuck, go online, see if somebody wrote a blog post where they explain how this paper works in their own words. But keep in mind that if there are things that are confusing in the paper, these people may also have made choices that are not correct, because they also may have had to guess what the right answer was. So just because someone wrote a blog post about it also doesn't mean they know or they understand the paper fully. And like I said, you can always email the authors for clarification if you really are stuck on a paper. So there's lots more I can mention about this particular filter and how it turned into a plugin. You can read about it on my blog. The main reason I mention this is that even if you were able to implement a paper into code, it doesn't mean it actually sounds good, so you might still need to do a whole bunch of tweaking and fine-tuning. All right, so very quickly, I also want to talk a bit about patents. If you thought papers were hard to read, then, the patents are they're written by lawyers for lawyers. That's basically how that works. But just as it takes some getting used to reading academic language, you can also read to learn patent language. Now, you might want to read patents because you're worried that some existing patent might be problematic for your business. But for our discussion, we kind of want to read old expired patents for their ideas. And I'm not a lawyer, I'm not a patent lawyer. This is not legal advice. A lawyer will probably tell you not to read patents, because ignorance is bliss in this case. But I think we're okay if we stick to old expired patents. The best place to find patents is on Google Patents, because they index stuff from all around the world. And I want to quickly go through this patent from Casio about one of their phase distortion synthesizers. And this isn't a very old patent, so you don't need to avert your eyes. Patent has a title. This one is electronic musical instrument. Very vague. It's typical of patents. There's also a date at the top. This is from 1987, so that actually means it's very old. All these ideas in this patent are safe for us to use. So if a patent is more than 20 years old, you're probably okay. Just like a paper, it has references to previous work. That's like this section. You can find these patents on Google Patents using the number in front here. Just like a paper, it also has an abstract that summarizes it. And just like a paper, there will be images. In this particular case, this particular image, this patent has 40 pages of images. So I like to just open up 2 copies of the documents, put them side by side, and use one to read through the text and the other one to refer to the figures, because otherwise you're scrolling back and forth the whole time. And then there's a wall of text. Pretty dense. You probably need to read this a few times, but this describes how this invention works. And again, it pretty much follows the same structure as a paper generally. There's introduction section, there's a background section, talks about related inventions. There's something that goes into details of how this invention works. And there's something called the embodiments of the invention. And that's where they describe how to take the idea from this patent and turn it into an actual physical device. Because patents are not just about ideas, they're actually about physical realizations of this idea. And there might even be math here as well. Now, for our purposes, we probably want to turn these hardware patents, because most audio patents are about hardware, we might want to turn that into a software implementation. So we might be interested in these block diagrams. Probably want to skip these electronic diagrams. And this particular patent has nice pictures of waveforms and frequency spectra and so on. So a lot of the information is really in the patent. It's just that the language can be a bit hard to get through. A patent also has a claim section, but for our purposes, where we just want to study old expired patents for new ideas and insights, we can actually skip this section because it's like the least readable part of the whole patent. And this is really just for, for the lawyers. So we can safely skip this. All right, and that's me. This is where you can find me. I wrote a few books as well, and I continue to write on my blog, and I'm available for hire as well. So thank you very much.